technical issues, the internet is off.
I think we should continue with the next session, which is the session of use cases, hydrogen aviation use cases. And as first speaker, we have here Josef Kallo from DLR. A lot of everybody, I think, who think about aviation, flying, and hydrogen over the last years has heard his name. So, Josef, if you can give us an update, you want to share your screen, I think. It should be possible, and you should unmute your phone. Xin, perhaps you can. I'm the host now, so I have to hand over the host again. And perhaps all who are not presenters anymore, if they could switch off their cameras, because then we will have a camera for Josef again. I see Josef, have you unmuted? This is the reason. Kallo, Josef, no, audio. Now you are.
Think now I'm unmuted. Okay.
And I'll leave you the stage for you, and I will go off.
Okay, so first of all, thank you very much. I have a short presentation. Willy, you have just to tell me how much time I have. So how many minutes, just roughly?
Roughly, I would say 15 minutes. We're good in time, and it's always very interesting. We have, if you can talk about 15 minutes, and then we have a Q&A later as it works in a breakout version. Okay.
Okay, so emission-free flight with hydrogen. I will accelerate a little bit. So I am responsible at the German Aerospace Center for the Department of Energy Systems Integration at the Institute of Engineering Thermodynamics. And we deal there with battery systems and fuel cell systems. And we are experts on hydrogen implementing systems into aircraft application. We also have this H2Fly, which is Hydrogen2Fly startup out of the DLR, which owns the HY4 and also takes care about the overall propulsion design, including the electric motor. The electric motor itself is developed together with our partners at the university where I am the director of the Institute of Energy Conversion and Storage. And there we do motors between 180, 190, 200 kilowatt and up to megawatt level. So with this together, I will focus today on the hydrogen fuel cell propulsion system. So we have definitely the classic point with kerosene and gas turbine. Then we have the most improved with kerosene, hydrocarbons as fuel, even with hydrogen as a fuel and gas turbines, and then an electric generator and hybridized by batteries with an electric motor. Today, I will focus on the hydrogen use in fuel cells together with a battery, if needed, to propel an electric motor to go flying. So why are we doing this? What we know is definitely that, as an example, in Frankfurt, we have from all those 46 million passengers per year, not last year, but in 2019, we had almost 20 million passengers flying in from less than 800 kilometers. So in 2033, we will have expected 91 mega hubs due to our colleagues from the German Aerospace Center with more than 500 million of passengers, which will fly in from less than 800 kilometers. So there is a huge CO2 saving if we can minimize the emissions by flying with a fuel cell. I will go into that 800 kilometers later. Also, if we can have a plane which can fly less than 2,000 kilometers, we will skip more than 50% of the emissions. So what you see there, the thin curve is the fuel per distance bin. So going there and integrating all those numbers until 2,000 kilometers, we get much more than 50% in fuel burn, which goes into emission. But to go into this, we cannot fly with 4-seater or 10-seater. We definitely have to go bigger. And we think that it's crucial to go to bigger, let's say to 150 passengers. But from a realistic point of view today, we think that a 40-seater is feasible. My colleagues from Göttingen and Braunschweig calculated some ranges. And if we take the 328 with improved wings, we definitely have a chance to go roughly, if we have a system energetic weight of 630 watt-hours per kilogram, where every battery is far away from reaching that, we can go roughly 1,000 kilometers at full payload, maybe 750. And what we expect to be realistic with liquid hydrogen and fuel cells, including the motor, is to achieve 1,200 watt-hours per kilogram, having a range at full payload of 1,500 with a little bit less payload at 2,000 kilometers. There is also another possibility to store hydrogen in liquid. Unfortunately, that is not certified, and there was just one test specimen tested, and there are some challenges with the boil-off. But I would say from a realistic point of view, we should stay around 1,000 watt-hours per kilogram in the next couple of years. Also, my colleagues have done a lot of development on the conceptual side, from classic applications with twin engine to more sophisticated with twin engine and wingtip propeller with distributed propulsion. And what we have seen is when you take a 70-seater, let's say baseline TPR 70, which we have today, turboprop 70, which we have today, by only improving with new engines, which are today, let's say, the last generation, we can save a lot of fuel on the fleet. Then putting some hydrogen and also some hybrid planes with wingtip propellers and improved aerodynamic efficiency, we can go maybe to 35 to 40%. And if we go to distributed propulsion, we can have a short takeoff, but we pay for that a penalty in efficiency. So we have to do a trade-off what our mission would be like. So what we think is that as a baseline, we have a chance to go into a 40-seater regional aircraft, around about 2 megawatt combined hybrid propulsion power, even a little bit more than that. And we need an approximately cruise of 1.3 megawatt. With that, we can go up to like 250 knots. And depending on the kind of fuel storage system which we implement, if we go with a 1,200 watt hours per kilogram, we could scratch the 2,000 kilometers in range by improving
续航里程，而且过程当中，前提是呢，它的
which kind of other applications? So I have done some with my colleagues from Hyfly. They started thinking about how to put these applications into place, how to use fuel cell and hydrogen. And what we see is that going into like VTOL types airplanes, around about peak power 350 kilowatt, maybe cruise power at 200 kilowatt, we can reach a range of realistic 150 to 180 kilometers without reserve around 250 kilometers. That would be the maximum for today's perspective. Going into general aviation, taking a 6-seater, you definitely can go to like 1,500 kilometers. We just finished the work on the HY4, so on the hydrogen plane, which you see in my background. And we will have a new press release on Friday on that and the presentation of the plane. But we can go with general aviation, I would say roughly 370 kilometers an hour up to like 1,500 kilometers. And on the 40-seater side, a new concept in parallel to what I developed together with the University of Stuttgart, shows us that we need a peak power of 3 megawatt, and then we will go with a cruise power around about 1,400 kilowatt, and we can go 500 kilometers an hour, a little bit more than that, for more than 1,000 nautical miles. So this converges together, and this would be, I would say, the realistic path for the next 10 years to go with hydrogen and fuel cell system. Challenges with that are definitely the storage system, gravimetric energy density, which at the moment can be elaborated at realistic 28%. More than that, it's feasible, but the problem with that is that it's not certifiable from today's perspective. So there a lot of new work has to be done, engineering focused on certification and qualification. Also, due to the new arrangement of the systems, the center of gravity and the cooling system implementation has to be taken care of. And very important, the energy distribution system, which should have more than 1,000 volt, optimally around, for this power, around 1,500 volt, maybe a little bit higher. What we have to take care about is the insulation, and we all know that the insulation and the breakthrough voltage and also the corrosion and the corona effects are taking place when the geometrical shape of the conductors is not well built. So in that case, we know also that the Paschen law, when we go to high altitudes, can go to a breakthrough depending on the geometric shape of the conductors and depending also on the altitude and the pressure there of the air. And then we see that if we stay very low in geometrical distance between the conductors, we even can have a breakthrough at 700 volt, maybe at 1,500 volt, depending on the geometric. If it's parallel, it's higher. If it's with edges, with sharp edges, is lower. So this is something which has to be implemented in the complete architecture of the energy distribution system. Also, every component has to be taken care of, not only by having high voltage, but also by having certifiable components, which means that we have to go into a lot of work to make them lightweight and certifiable. So with this redundant hydrogen electric powertrain based on the ARP 4754 process for the HY4, which I can say officially will be disclosed on Friday, but we had a lot of very good testing in flight with this. We see the hydrogen system, which is redundant. Then we see the fuel cell systems, which are redundant. And very important here, a lot of logic into the power module control devices, which are steered by a DAL-A controller. And then we have to go into redundant motors. And the powertrain design, not only the fuel cell design, but also the overall powertrain design, when we want to go to a 40-seater, we have to really take care about all those points with the high voltages and the insulation and the geometrical shape. So it's a challenge, but from our perspective, it's feasible. So taking all those things with process, with sensors, certified, qualified components, going into certification and qualification, we have also to take care about the operations. So if hydrogen spilling is there, what will happen with that hydrogen and so on. So what we need is a worldwide qualification base to qualify the concepts, the modules, the powertrains, and at the end, the plane. So what is the gain from that? What you see here is the sensitivity of the perception of the human ear. And what we see here on the x-axis is that at 1 kilohertz, between 500 and 1 kilohertz, we have a very high sensitivity of the human ear. There, the turbines do a lot of work. Then if we go down to, let's say, some engines with combustion engines, we definitely can go down to something like maybe 50 hertz, maybe in the region of 100 hertz. But if we have a chance to go with the fuel cell plane, even to due to the high torque of the electric motor and the propeller, which is not a high-speed propeller, but can be very slow turning, then we have a chance to go to lower frequencies, and that can be a high gain on that. So the next gain could be to go with renewable energies to produce the hydrogen, and then based on that to fly around. Just to give you the numbers, in Germany, we had used kerosene worth 105 terawatt hours. And to compare that with the surplus of energy which we expect from renewables installed in 2018, we know that the perspective for 2030 is to have something like 35 terawatt hours per year. And comparing that with 105, which we are using today, and definitely this is also for long range, for short range, and so on. But just to give you a comparison, this, including 100% conversion efficiency, which would not be realistic. The conversion efficiency from electricity to hydrogen is roughly 65% in a very good electrolyzer. We definitely have to install not a lot of new renewable energy, solar and wind, to produce the fuel which we need for flying around electrically with hydrogen. I'm very confident on this because I have seen that wind in the US became very, very cheap to be produced on ground. So we are talking about $32 per megawatt hours, even in best places around less than 2.5 cents per kilowatt hour, or $25 per megawatt hour. And if we calculate that in fuel, including the price of the investment, we see that we could fly with renewable hydrogen at around about €3 per 100 kilometers per passenger if we go into a 40-seater. So comparing that with something like 1.5 to 2.5 euros per 100 kilometers per passenger in a turboprop, that is not far away, but it's still more expensive. So to summarize my work, I think the hydrogen fuel cell propulsion for passenger airplanes is feasible for a 40-seater from today's perspective. Even bigger airplanes, maybe up to like 140, but that would be passengers, but that would be a vision, I would say. And from today's perspective, with a storage system which we know today, which can be certified, we can reach 2,000 kilometers of range. We can reach higher range with other systems on ground, but from our perspective, there is a lot of work which has to be done to get them certified. So on a megawatt scale technology, we have to work. So definitely we have to change from hundreds of kilowatt to megawatts and a lot of megawatts. And then we will get a lot of CO2 reduction potential. But we have to take care about the balance of plant customization. So there, definitely, the focus has to be on for the next 3 to 5 years. And then the integration, taking care about the thermal management and the voltage management are crucial to go into the homologation. With this, thank you very much for your attention. There was a lot of support from European and German funding schemes. The Ministry of Transportation, the Ministry of Economics, and also from the European Commission directly. And thank you very much for all the partners. I have to mention my colleagues from the DLR, my colleagues from the university, from the H2Fly, my colleagues from Diehl Aerospace, and also from Pipistrel, and from the airport of Stuttgart, which we worked together to achieve a part of these results. Thank you.
Thank you, Josef. And like always, it's very interesting stuff, and I would like to hear more, but then we would sit here all day, and you also don't have so much time. Thank you again. And perhaps you can remind us again, you said you will have some announcement doing later, I think even later this week, so that the people perhaps may join, or when they can expect it.
Yeah, so we will have a presentation of the 6th generation of the hydrogen fuel cell HY4. And this would be on Friday this week at 1:30. and I will send you, Willy, a central link so everyone can then check in on that link on the h2fly.de page.
Super. Definitely great. And we continue. Thank you very much for joining, and hope next year we see us again in real China with a real trip.
Yeah, hopefully.
And not only virtual. Our next presenter is Phillip Scheffel, CEO of the company APUS. APUS is doing different electric aircraft and also working on hydrogen aircraft. So Phillip, I think you should be among the audience. We got, at least I've seen you before. So if you yeah, I see you. Ah, perfect. Very good.
Okay.
And I think you will share your screen.
Yes.
The microphone is a little bit low noise, so perhaps if you go a little bit closer, it's better to understand.
Okay, can you hear me?
Now it's good.
Yeah, okay.
Okay,
And you can...
Screen is coming and I go off. Talk to you later.
Okay, I just arrived in the convention and had the pleasure to listen the last part of Josef Kallo, whom we know very well. He is really the pioneer in this field of hydrogen technology, and we appreciate very much to have from time to time some consultants with him. He's of course the one who's doing the basic research and delivers the basics we build on. What is APUS? APUS is an engineering design office close to Berlin in Germany and in the east of Berlin, and we are actually designing aircraft systems. It can be a structure, it can be full-scale aircraft, everything that is needed by OEMs. So normally we are working for other aircraft manufacturers, and this is from the sport aircraft until the drone or multi-seat aircraft, everything. We are EASA Part 21J approved, so we have some privileges until performing flight tests by ourselves, and that's what we are doing also in the past. Additionally, we are 9100 certified, and we are short before a Part 21G certification. That doesn't mean that we want to be an aircraft manufacturer in the future, but to qualify our prototyping, we need that. So that's for APUS. And next to a lot of programs we do with our customers, we have an own project running since almost 5 years on the basic research, and that's also related hydrogen propulsion systems, and that's, I think, the reason why we were invited here. And that is how the program looks like. In our engineering life, we see a lot of different technologies, and we are able to compare them quite well. And in this surrounding, we found that the hydrogen propulsion system definitely has a future nowadays compared to battery electric aircrafts when it comes to range. And there's no other technology at the moment that can compete when we talk about emission-free flying. I think this is also clear for many of them, of us in the meanwhile. And yeah, of course, there are big challenges. Most challenges are around the fuel cell itself, where Josef Kallo is working on, but the other big challenge is how to store the hydrogen in the aircraft, as it is a very light gas that needs to be compressed or cooled down. In small aircrafts, we have a problem to cool it down because we need a lot of isolation of the tanks, and we don't have the volume for that. So that's why we decide here for compressed hydrogen. And of course, we want to keep the fuselage free. So our solution is to store the hydrogen in the wings. So to do so, we need a certain volume in the wing, and that means a totally new aerodynamic concept for this. You need an airfoil that can contain as much as possible volume, but is still capable to cruise fast. And there we did basic research in the last years, and I think we found an optimum for such a twin engine aircraft. To store the hydrogen. The aircraft itself will compete in the class of in the lower 4-seat class aircrafts. So let's say Cirrus SR20 can be a competition. And what you see here, the weight, the total weight will be higher than the competitive aircraft due to the higher structural mass of the hydrogen. There will be a 6-seat variant of it. So once the power density of hydrogen fuel cells goes up, we can, so we need a little bit more takeoff in this case. We can also, the fuselage is big enough to contain 6 people. Just to give you an imagination how it looks like in comparison, here's the Diamond DA62, the comparison. So the size is more or less like that. And yeah, the DA62 has 7 seats nowadays, 6 + 1 small seat. The system itself is fully redundant. That's something we need to do nowadays to get the first step into the door of certification, because we have a quite complex technology around the electronics and also the hydrogen systems. And we want to use all the redundancy benefits that we can get from the twin engine. So we have 2 electric engines, 2 fuel cells, and also by the emergency hydrogen fuel tanks, we are fully redundant in the systems. There will be some means for the hydrogen system. There will be a high pressure system, a middle pressure system, low pressure system, all controlled by a hydrogen and energy management system. And yeah, some details we will discuss in later stages. But what you can see here, the general concept, we will have a rectangular inner wing to be able to produce cylindrical tubes at that length. The inner wing is 9.20 meters long. That is more or less triggered by the size of available autoclaves, because the inner wing is produced in high temperature prepreg materials. So everything is on the inner wing is high temperature carbon prepreg. Yeah, that is the outer wings are then aerodynamically necessary to give at least a little bit elliptical lift distribution. But that's also some penalty we get the relatively big wing, and that results in comparable a little bit lower cruising speeds than competitive aircrafts have nowadays. Of course, a big topic is the energy management itself. Also here we have long time research on mathematical algorithms. This is only an example now for the PowerPoint slide. It will look definitely different, but here we are working with universities and ourselves, a small team on the system, how to distribute the energies, how to track the lifetime of batteries and so on. This definitely needs to be done. And yeah, it controls the energy flow. What you can see here, we will have all the electronics, basic electronics in the nacelles themselves. So we have electric motors, the controllers, and the batteries to compensate the hysteresis of the fuel cell directly in one nacelle. And the hydrogen fuel pipes goes there from the wing and from the front. Yeah. Okay, here again the concept of the hydrogen storage. I think this is essential to make hydrogen available in the lower weight classes of aircrafts. We see a break even of energy density somehow around 2 kilowatt-hours per kilogram. That's something we have to achieve. With high pressure systems in cars nowadays, we reach around 1.6 kilowatt-hours per kilogram. And it cannot be increased very much anymore, because there's the fibers are loaded by tension, and there's a limit of the carbon fibers, and this cannot be increased anymore. So how you can increase the the energy density is by structural synergy. And our concept is exactly that. And when we use the tubes as the bending beam inside the wing, we can reduce the weight of the tanks by the virtual spar. So the tank itself will be lighter. And yeah, this is how such a wing looks like when it's built. And the biggest challenge, to be honest, here is the manufacturing process. How to build such long tubes, how to make the end of the tubes, the pole caps, strong enough, and how to make it safe enough from the structural point of view. Yeah, the safety concept for the fuel cell itself, of course, we have designated fire zones on many places. It's always the biggest problem in hybrid electric propulsion systems. You have the propulsion system distributed all over the airplane. You have pipes and fire it can cause fire, and our concept is yeah, there was an echo now, but over to separate the fire zones, so that even a fuel cell or components here, converters are here too, can burn without affecting the other side. That are the aerodynamic and the weight data. So we have a span of around 12.6 meters. And the wing with 18 square meters, slightly bigger than comparable aircrafts due to the higher maximum takeoff weight. For the 4-seater, 1.8 tons. For the 6-seater, almost 2 tons. We want to stay below 2 tons intentionally. Definitely the hydrogen systems will work on heavier aircrafts too, but as we are here at the stage where we first time want to achieve a full certification, we want to keep the budget as low as possible by the maximum takeoff weight. Is it me the reason for the echo, or comes from somebody else? No. Okay. That's the time schedule for the moment. So we are working on the program, at least on the basic research, since 2015. Since beginning of 2019, we are concepting the aircraft. This is done more or less. We are in the detailed design phase nowadays. We are also developing the fuel cell system and the propulsion system nowadays. This is on the electric side also running since a while. And of course, this is not our experience not only come from this program, but we are working since some years on different electric propulsion aircrafts. For example, on the Extra 330, at that time it was Siemens aircraft. We work on this aircraft still to make the retrofit with electric propulsion system. We are working for Safran, working for Rolls-Royce. Some of you know the APUS i5 program, a hybrid electric propulsion system, and we are developing and integrating the system, the propulsion system, and some smaller aircraft manufacturers we are working for. Yeah, in the competition, I said it already a little bit earlier. This seems at the moment, at the first view, a little bit disappointing. Why we are not competing directly with an DA62 or Cirrus SR22? Yeah, because it's simply not possible at the moment. The power densities of the systems are still too low. The basic weight of the propulsion systems are too high, and the penalty we pay is the cruising speed and the range. Nevertheless, I think a cruising aircraft makes sense from a range of 800 kilometers, something around that. The battery electric propulsion systems are far below. We are at least at 1000 kilometers. That is quite good, I think, for an electric propulsion system. Also, the cruising speeds are competitive. And the big advantage that we have with hydrogen propulsion is the high payload, because we don't have to reduce the payload by heavy fuel. It is when we when the tank is full for around 4 or 5 hours, we refuel it with 25 kilogram of hydrogen. So this is only reduced by 25 kilograms, so 450 kilogram payload for a 4-seater. This is quite comfortable. There will be different products, of course, at the end. This is just a first idea how we can have the road to market. So just some mentioned prices. We will be the systems are quite expensive, of course. So at the very beginning, it is not really a competition to the conventional aircrafts, but definitely the systems will be cheaper in the future. This is also our big hope on the fuel cell. As it becomes a mass product, the price will go down, but the first aircrafts will definitely have prices like that. That are our partners nowadays in all the programs that are running. Of course, it's supported by the German government, by regional governments, fundings, and the rest is completely financed by ourselves. And yeah, we are using fuel cells at the moment, a stack from PowerCell at the moment. Yeah, we will see what are the better systems in the future. Fraunhofer, Rolls-Royce for the electrical propulsion system. And on the structural side, we're working close together with our supplier Cotesa. That we have a long time strategic partnership with them already. Yeah, this should be the short presentation of our product. I hope it's exciting for you. We are always looking for partners, for potential investors, definitely. So just come in contact with us. And of course, any comments, any feedback from the market, from potential customers is welcome. And yeah, would be happy if some people contact us. Thank you.
Thank you, Phillip, and very interesting project. So when we were thinking about like use cases of hydrogen, actually we didn't really think of something which can come to the market and it looks like an aircraft which you can buy and you can fly. So we are definitely, it's an amazing project you have there. And before we go to any further questions, I will hand over to our last speakers of the session and the day, and then we can have, I would say, a normal Q&A session, as not everybody could join the rooms, and then we can have the Zoom rooms again, where we could talk more privately with the presenters. So thank you very much, Phillip. And our next presenter is Klaus Ohlmann. Klaus, if you unmute your camera and your microphone. We've seen you before, but now I don't. Now I see you. Yeah, the microphone is unmuted, but your camera is still. Here we are. Hello, Klaus. Yeah, in Corona yet it didn't see so often like normally, like Aero and others. So Klaus is coming. We had very different approaches to electric aviation. We had industry, we had the academics, we had the authorities. Klaus is a pilot. In first line, I would say he's a pilot. He's also is a researcher, but he's a pilot with a whole bunch of world records. So Klaus, tell us what you plan with a hydrogen plan.
Hello, everybody, and welcome to China and our internet audience. I'm a glider pilot. My motor is based on the principle of gravitation, and my energy source is a very powerful fusion reactor, our sun. Flying in a glider is a little bit like a dream. You transfer constantly altitude and speed. The lost height you will regain in thermals or dynamic lifts. That allows us to fly unbelievable distances of hundreds or even thousands of kilometers. There's just this small amount of fossil energy we need for a winch launch, an aerotow, or a self-launch. necessary to climb to the initial altitude before starting the soaring performance. This little dirt under the fingernail was always a thorn in my side, disturbing the perfect image of a zero-emission flight that you can do with gliding. But how to do better? 10 years ago, I could participate as a test pilot in the e-Genius project. This was a fully electric prototype which was built from the scratch by engineers and students from the Institute for Aircraft Design of the University of Stuttgart. They finished in less than 2 years a battery-driven electric plane, which is still, until today, the best electric aircraft of the world. With this plane, I could fly 6 world records in distance, speed, and altitude. They are still valid until today. 2 years later, we flew a spectacular crossing of the Alps from Stuttgart, Germany to Italy and back, nearly 700 kilometers in one day. Energy costs around about 21 euros. Lightweight materials like carbon fiber composites and the big advantage of an electric motor in aviation with its fantastic power and volume to weight ratio allows much more freedom in aircraft design than ever before. The modern electric engine has around about 4 times more power in much less volume compared with our usual combustion engines. Better efficiency of airframes and propeller can easily cut the consumption to nearly a half compared to conventional aircrafts. Energy storing in nowadays batteries is highly efficient. That sounds perfect. But are there not any drawbacks? Unfortunately, there are. First, batteries are heavy and have a low specific energy. 1 kilogram of kerosene has 50 times more energy content than 1 kilogram of a modern lithium battery. The price of batteries is still quite high, even if it is decreasing. The time to charge batteries need at least 3 to 4 hours. Range is one of the biggest problems of air taxis today. For longer flights, you need a range extender, which could be a small combustion engine as a generator to charge a smaller battery pack and replace the gain of weight with fuel. All calculations show a significant reduction of fuel consumption. But what about zero emission? The zero emission solutions are fuel cells, powered by green hydrogen. There is no doubt. Hydrogen makes only sense if it's produced with renewable energy. Local electrolyzers can do the job via solar panels on hangar roofs. This is what we are working on. Electric propulsion and fuel cells are the perfect tools for a real sustainable aviation. Very low noise and no vibration. Once you have flown in such a plane, enjoying the comfort of such a silent flight, you will find it difficult to go back to these fuel-to-noise converters we are flying today. Hyfly is a great team, and I am proud to be part of it. Karl Käser, one of the project managers of e-Genius and now owner of Casa Aero Engineers Bureau, is responsible for integration and certification of ultralights, air taxis and planes. Peter Statthalter, owner of PS Hightech, is a specialist for light, extreme light hydrogen tanks, fuel cells and hydrogen infrastructure. And last not least, my glider will serve as a test bed for this disruptive clean technology. And here I start to dream. I'm convinced that only technical knowledge and progress will solve a lot of climate problems we have today. An emission-free flight from Germany to the Himalayas, soaring above the top of the world, creating beautiful pictures of a wonderful glider in stunning landscapes.
Changing fear for our climate in fascination and hope. Let me finish with Franz Kafka. Paths are made by walking.
Thank you for your attention.
Now I understand why you wanted to play the video. I think you're muted. You have to unmute yourself. Where is he? Klaus. Klaus, you're still muted.
Now it's better?
Now it's better. Much better.
Okay. Oh, sorry for this. I had some problems to see the video. I hope in other parts of the countries it was a better internet. And you could see the video and hear the music. So my part is the emotional part. So I'm a pilot and a very emotional, and I'm absolutely fascinated by the possibility of green flights. And I hope really that in the near future we can do such beautiful things, flying around the world, flying in high mountains with the help of emission-free technology.
Thank you very much. I think I go back onto the stage again, and I would ask also the other two persons, because we are finished with our presentations for today, and I think this was a perfect closure of starting with the paperwork in the very first session and having the dream of flying in the last one. It really is a nice progress. And after several hours, I think this was perfect. So perhaps Phillip and I think Josef is still available a little bit. I'm not sure, because he had a time limit, so maybe he would have to leave already. But Phillip, if you could come back on again, and then we could have some questions and answers, please. Phillip? Seems to be... I have to look for him. This is a little bit difficult. Then what I would say is then we Scheffel. Phillip Scheffel, is he still? Let's have a look. No, it does seem that he is not anymore into the presentation. I think he also said, yeah, probably he has some other appointments which he couldn't shift. I think I remember something like this, so it's my mistake. So, okay, then I would say perhaps we could have, I see Florian Hilpert is still in the call. Have those people who are who have been presenters and who are still there, if they could come switch their video on and come back on, because then we could start with questions and answers. I have several, but so I don't see. We'll see. If some people come in addition, that's good. If somebody of you has questions, just ask them. There have been questions before. I'm just scrolling through the chat before. This was just remarks. The question would be if the distributed electric adopts air cooling and no air entries, the controllers components, how to guarantee the life under the maximum continuous power. And I know I see there was the answer here already. Thermal management on the.
Yes, but I can.
Yes.
I can comment.
Okay. Yeah.
If
No.
you want to. Yeah, the thermal challenge for power electronics is really a big challenge. Power electronics are, I said it before, are sometimes seen as standard electric components, but they are not. They are highly mechatronic integrated systems. And in the breakout room, I have told about this. About half our engineering staff is mechanical engineers working on power electronics. So we have no power electronic project where we have a mechanical engineer missing. Even the head of our inverter development department at IASP is a mechanical engineer. Because with these new silicon carbide and gallium nitride, the wide bandgap fast switching devices, with these new devices, the mechanical design of your power electronic system has more impact on the electrical behavior than the electrical design, actually. This is really counterintuitive, but how do you explain best way? The parasitic components inside your electric systems, they get so dominant and they are defined by the mechanical design of your system that it's really more a mechanical challenge to build a large integrated power electronic systems than an electrical challenge. It remains a large electrical challenge regarding failure handling, of course. If you have like multi-phase failure redundant approaches, this is electrical design, but the efficiency is the mechanical problem. And with the efficiency, we come back to the thermal topic. What was the question referred to? You really have to simulate your entire power electronics systems from the environment down to the device itself. And it's especially tricky for air cooling, because with water cooling it's easy. You have a defined flow of the water, you have a defined temperature mostly, but with air cooling you typically have to consider all the transient situations that can occur, and therefore it's really necessary to build a complete digital twin of your power electronic system and then simulate from the environmental cooling situation down to the device itself. So the system level engineering for the thermal design is crucial here to have air cooling for high power silicon carbide power electronics.
Okay, thank you for the
really
extensive answer. And I would say now those people who want to ask a question, if you switch on your screen and then you can ask the question yourself, because just if you want to ask a question, you switch on your screen first image and then you talk, and this gets us a little bit more interactivity. I have a question here from Olaf, who was asking before. Olaf Otto, how you can work with Rolls-Royce, and it was a question for Olaf. How you can work with Rolls-Royce in an airplane project? Are a Rolls-Royce motor for sale, or just for projects now? And so Olaf, if you're still in the call, would be great if you can join. Otherwise, the question does not let me search. Olaf Otto, he is still in. Olaf, I'll ask him Stummschaltung auf. I ask him to unmute himself, but he is at the moment not. Probably he has some other conversation at this point. Sorry, I have to write him in the chat, so maybe we have the question, the answer for this question later. But I know that they are ramping up for the product for sale, because in his presentation he is selling that they are have the product now and they do pricing for the product, and they say research was one part, but now we have to make it the research to a product. I see you, Peter. Do you want to ask a question? Okay, then I would say I unmute. So I think you can unmute now yourself. Yeah, now you are.
Okay, how it works. Thank you very much. Question to Florian. Hi Florian, my name is Peter Statthalter, PS Hightech. I'm located not far away from Erlangen. It's half a little route this way. The question is, are these power electronics systems, are they already available? Can they be purchased, or what is the actual state?
So our power electronics systems, they are typically research prototypes, because we are a research organization. Fraunhofer is one of the largest research organizations in Germany, with a lot of institutes. So our power electronics, typically they go, they stop in the development before the manufacturing for end customers. So we do the development all to the way where one of our customers can then proceed in the series production, but with the series production we are not involved. The background is Fraunhofer has some percentage of its revenue as base funding from the German government. And this is why we are not allowed to compete with engineering suppliers that can go and sell, like, for example, power electronics. So we are only able to sell, let's say, power electronic prototypes for test bench applications. But we can go through a series development together, where we supply with engineering support throughout the series development process. But our customers are the ones that really produce the power electronics and sell them in the end.
Okay, is there one certain producer of your power electronics in this moment?
Actually, we are working with, let's say, all companies in Germany that are dealing with power electronics. For example, if you go to the automotive sector, we are delivering typically the prototypes for their very first test fleets, where they need like 20 power electronics for a certain vehicle, because the large manufacturers, of course, they won't build a dedicated power electronic for a new vehicle in number 1 or 20. This is the niche where we really supply the systems, and typically they then take our prototypes to a manufacturer, show them the prototype and say we want something like this. And typically these manufacturers then come back to us and ask us, okay, how did you do this? And then we try to figure out a way to adapt it to their manufacturing processes. So this is typically the way how they go into the market.
Okay, I understand. Thank you very much.
Okay. I have a question to those from those people which are in the fuel cell area or in the hydrogen area. What do you think about this project presented, this liquid LHCA, the liquid storing of fuel cell of hydrogen in oil? because this is for me, it really seems to be something. I heard about this some time ago, but do you think that this is something which is really could be on the market fairly soon? Because you're working with hydrogen, so you must have had thought about this. Florian, I was just asking you.
The storage of hydrogen is really one of the key problems to solve, especially the supply on site and how to fill up systems with hydrogen. I personally am not involved in this. As I said before, we are around 70 Fraunhofer institutes, each institute dedicated to certain topics. But where I am involved a little bit is in what we have heard before from Hydrogenius, the LOHC technology. It's close to what you're mentioning now, so storing hydrogen in a liquid carrier. And the LOHC was presented excellent by Hydrogenius, actually, also with all the challenges that lie behind, especially also regarding power density. At the moment, I also think that it's very useful for stationary application where you can store it on site, then extract it on site and fill it in maybe a pressurized or liquefied, let's say, vehicle. But for let's say mobile applications themselves, like aircrafts or cars or so on, the power density is at the moment really, needs to be addressed more.
No, the question would be only, I think, as I understand there, right? It would be more for the storage at the airport or for the storage at some other fields, because as I understand, also he mentioned that if you have the liquid and you want to get the liquid, the hydrogen out of the water, out of the liquid again, you have to have energy. And this is a process that probably you don't want to have on board of an aircraft, but because it will be complex and heavy. But just for storing outside, I think it may be interesting.
Absolutely, and if you could integrate it in an overall thermal management for a large facility, where you have, for example, you have waste heat from some cooling infrastructure that you can then utilize for the LOHC process. This is really would have a great impact.
Okay, at this point I would have one question to Klaus Ohlmann, because we've seen at the end of the film that you say you start dreaming. Are there any concrete projects which you're planning, what you want to do, and where we can expect to see in the news at some point that somebody has flown a rocket with a hydrogen aircraft? You're muted. You're still... Klaus, you're still muted. Aufhebung der Stummschaltung.
So now you hear.
Now we hear you. Yeah.
And no, not again. Klaus, you're somehow muted again.
Yeah, Klaus, you're.
Again.
I think it was my mistake. I was not patient enough. Like my son, when he presses a button on the computer, he always hits it 10 times, and then it's on, off, on, off. It's yours, Klaus.
Yeah. So my part is to emotionalize all these technologies with beautiful pictures, with things to do, and you spoke about the passion. I have not too much passion to waste all these new technologies. So I would like my STEME as a test bed, because it's a really very nice plane to do that. You can make an electric motor in front. You have a lot of space behind in this tubular structure, the STEME. So I hope to fly, let's say, in 6 months with an electric plane, actually, and then I would like to use it as a test bed with probably a combustion engine at first as a range extender, because as I mentioned in the conference, we need more energy than the batteries can give us nowadays. So when you want to fly more than 1,000 kilometers, that's, from my opinion, the minimum that you need to fly around the world. So I'm thinking always big. So what I would like to do is to start with world records. Anyway, there are a lot of world records to break. I started with the e-Genius from the University of Stuttgart. Probably I will fly another project with an Antares, an electric glider, which has another system to make bigger ranges, but still they are limited up to 400 kilometers. And at the end, that's what I see is anyway the hydrogen, because the full circle that you can make is without any emission when we use renewable energies. And so, you know, we have a lot of discussion about climate and so on, and I call it always the baseball players, because we work with fear nowadays. That's what I mentioned. I would like to work with hope, with beautiful pictures, to motivate people to change that, because we heard about, from Josef, we heard that the costs of these technologies are quite higher, still quite higher. But, you know, when you are in the desert and you have nothing to drink, you would pay $10,000 for one bottle of water. And when we are looking for our climate, I would like to motivate people to change that, to pay much more money. Nowadays we use bio foods and so on. And that is my idea behind. And I'm happy to work with engineers like Karl Käser from Hyfly, who is responsible for the certification stuff and technological stuff, and Peter Statthalter, who is the man from the fuel cells and infrastructure as well, because all these things have to be together. And my part is to emotionalize, to convince politics, technicians, and not the citizen to apply for this new technology.
Well, yeah, thank you very much. I just had to check if I'm muted. No, I think what we may do now is we either have another breakout session, and I think there is an option here where you can raise hands and vote, or if we continue with an open Q&A session. So please give me your, I think... Perhaps a question? Olaf. Olaf is back. That's great. Then we can answer the question which we had before. It is how can the question was how can we work? Can I work with Rolls-Royce in an airplane project? Are Rolls-Royce motors now for sale, or are they prototypes only?
So the propulsion systems that we have, they are prototypes. We are working together with partners in projects. It's by nature quite limited because we want to focus on a small number of partners who are working on bringing their products to certification. So something that was shown in the press fairly recently, for example, is our collaboration with the company Tecnam. In the commuter class, it's quite limited. In terms of having the equipment for use in projects, the easiest way is just to get in touch with us and to discuss it. As I said, the number of projects that we're going to run in parallel is going to be quite small over the next few years. We sort of come from a past of doing sort of 10-20 projects at the same time. We're consciously now slimming this down as we're focusing on product certification for our products. So get in touch, let's have a discussion, and even if we can't support you right now, maybe then we can support in the future.
Okay, thank you for the detailed answer. We will have a little short section with breakout rooms later, but I was a bit scrolling through our audience, and I saw several very interesting people there which we had as presenters in the recent years. So I would definitely try to ask Karl Kether a question if he's still in the call, because he was mentioned by Klaus before, and I know that he is working on several electric projects, and he will, or there will be some of the projects also presented tomorrow. So let's see if yeah, here he is. Karl, if you unmute, we are nearly perfect, and I think I have to find you probably, and I have first to give you the permission because we Anforderung, Aufhebung der Anforderungen. Yeah, so that's fine now. Yeah, so
okay.
So now it works. So yeah, so I know that you work on several projects. I know that several are under NDA, but we had, for example, last year presenting, you was presenting that you're working on the e-Aviation commuter project. Then we have, I think tomorrow, some of your team are presenting something else. So perhaps give us an overview, which is also a teaser for our guest to stay in and to join in for tomorrow again. By the way, the connection link for tomorrow is exactly the same. So when we finish here tomorrow, you click the same button and you're back in.
Okay. Yeah. Thank you very much. Yeah, that's a little bit short term for me. I have to scratch my head and think what I can talk about or what I cannot talk about. I mean, we are now on the, how shall I say, we are now on the way from experimental electric aircraft to certification of electric aircraft. Electric aircraft or even hydrogen aircraft, what Klaus has presented is the goal that we are working on with him to make a hydrogen aircraft reality and have it certified. Yeah, and our main focus at the moment and in the next years is to make certified aircrafts commercially available. Here in Germany we have the best conditions for this purpose around the world, I believe, because with the new German ultralight aircraft airworthiness specification, the LTFUL 2020, German ultralights are equivalent to light sport aircraft from definition. United States light sport aircraft would be equivalent to a German ultralight aircraft, and this new airworthiness specification released sometime in spring this year is the first airworthiness specification in the world, according to my knowledge, that includes requirements for electric aircraft, for electric propulsion unit. This is important, and this means here in Germany we can certify an electric aircraft without workaround with special conditions or equivalent safety or whatever. We just can straightforward certify, at least at the moment, two-seat light sport aircraft.
Follow-up question on this one, by the way, like I said before, if anybody of you has a question to anybody who has been on the screen or who is still on the screen, just switch your screen on, then we see it and you can ask the question. But follow-up questions, so actually two. One is, isn't there an issue that in this ultralight regulation the empty weight is a little bit challenged to defined in this new for the electric aircraft, so that it will be quite difficult to have an electric aircraft which flies a long time due to the battery weight?
Yes, I mean, this is a challenge. I fully agree. If you look, for example, however, I mean, if you look at, for example, Pipistrel's now EASA certified aircraft, the Velis Electro, it's in the same weight category. It has also a takeoff weight of 600 kilogram, but it is, yeah, so we let's say with this ultralight / light sport aircraft, we play in the same category, in the same weight category. Yeah, it's clear. So the weight problem is an issue. We have to address this from several aspects. First thing is, of course, reduction of the structural weight of the aircraft, improving the design. The second point is to improve the aerodynamic efficiency. When you look, for example, at the e-Genius aircraft, you can, and there are now enough publications on this aircraft already, you can see that increasing the efficiency is a big key of improving electric aircraft design. Yeah, it's very simple. You need less energy, you need less power to fly, you need less energy which you have to carry with you. So yeah, and the third thing of how we can address this weight limit is, of course, this approach to develop a lightweight fuel cell system with a higher energy density.
Okay, thank you for the answer. I also see, because if you look at our schedule, we're nearly over time already, and if so, for those people who don't want to participate in this, we start tomorrow at 9 o'clock Central European time again. And so if you liked it, tell your friends. If don't tell them. And I would like you to have you back tomorrow. We have interesting things to come up. Something, for example, Olaf mentioned very shortly in his presentation, the new commuter aircraft from Tecnam with Rolls-Royce propulsion system will for the first time be presented on a stage like this with international audience, and we will also have several others look at the schedule, and we even have some more than it in the schedule. So talk to you soon, and now I go to the break session and we'll see how this works this time, and tomorrow I hope to see most of you again. Thank you, bye. How can you get eFly Journal? Just scan the QR code on this page, or just type in your browser www.eflyjournal.com. Then you receive the page with the latest online news on electric flying, eVTOLs, and everything which is connected with electric mobility in the air. Or you can click the link on the top, and then you go to the latest PDF version, which you either can read in the Yumpu reader directly on your screen, like a conventional magazine, or you can go and download the magazine as PDF file so that you can read it offline wherever you want. Thanks for watching, and goodbye.